So let's kind of wrap up the normal distribution functions we started today. So it's a little more detail than I had in class. We'll do two of them. IQ scores are said to have a mean of 100 and a standard deviation of 15, be normally distributed. Adult female height is said to have a mean of 65 inches and a standard deviation of 3 inches. Now we started with a particular point in class. We did 110. And then we said, what percent have IQ scores below 110? And I mentioned that would be the norm.dist function. So there's your point, mean, standard deviation. And I forgot the true for cumulative. There we go. And we also did it backwards. We could say what's the 75th percentile? What IQ score has 75% of population below it? A little bit awkward wording. And then that is the norm.inverse. You go from the probability, which is right here, to the distribution. If you want to put it into percents, you can, or not. Let's put a little space in here. To a point. We'll do 67. And say, what percent are shorter than 67 inches? Since all of these references are relative in this formula, I should be able to just copy that. And that is not a coincidence that I came up with the same number. I chose those numbers on purpose. Oops, there we go. I chose that on purpose so I would get the same numbers in both places. And that's important because notice I didn't go a standard deviation, I went 2/3 of a standard deviation. But let's go ahead and go a full standard deviation in both. Oops. And you'll notice I get the exact same percentile because I went a standard deviation. Well, that's using these functions. What about these? I'm going to go back to my 110 and my 67. You may remember from a stats class something called z-scores. So you took a point, subtracted the mean, divided by the standard deviation, and got a measure in standard deviations. So for this point right here, the z-score for that is the point minus the mean divided by the standard deviation. I said it's 2/3 of the standard deviation. I said that before. Z-scores are commonly rounded off to 2 decimal places. This isn't really rounding off. I'm just rounding the display. But if I go over here, I get the same z-score. So it doesn't matter which of these distributions I'm in. If I'm 0.67 standard deviations above the mean, I get the same stuff. If I'm exactly 1 standard deviation above the mean, they both have a z-score of 1. If I go 2 standard deviations above the mean, oops, too far. There we go. They act the same, even though they're completely different distributions. And the fact that they act the same is what the standard normal is. The standard normal is called the z-distribution, or the standard normal. It has a mean, and it has a standard deviation. A mean of 0 and a standard deviation of 1. So if I want to do all the stuff I've done here, I would want to go, in this case, 2 standard deviations above the mean. And I get the same kind of information. And it's not IQ scores, it's just what percent of Z's are below. And the same thing for the percentiles. So let's go back and do the 2/3 of a standard deviation. Well, 2/3 would be literally, in this case, 2/3. And I get the same percents all the way. So the reason the standard normal exists is I could take any normal distribution, IQ scores, height, anything that's normally distributed, and if I can create z-scores for any questions about particular points, I can do it with the standard normal. Now notice I didn't use the standard normal function over here. I still used, if you look at these, and I'll put this out on Schoology so you can look at it, I'm still using the norm.dist and the norm.s.dist. So, or not the norm.inverse. So, let's use the standard over here. I did the z-score calculation. So if I wanted to find this same percent with the standard, I would say equal norm.s.dist, and all it asks for is what's your z-score, because it assumes you've done a z-score, therefore the mean is 0, the standard deviation of 1. And do you want cumulative? So I can go from a mean standard deviation at a point right to the norm.dist, or a mean standard deviation and a z-score and the norm.s.dist. Same thing over here, because it is the same. One more over. There we go. Since it's the same z-score, it's going to be the same result. If I want to go in reverse, let's sit back with the 75th percentile. Norm.s.inverse is give me a percent, and I'll give you a point. And it's 0.67 standard deviations. We already kind of figured that out, 2/3. If I wanted the 0.975, what's the top 2.5%? What's the bottom 2.5%? Well, it'd be a z of 1.96. So over here, this is telling me that this number, a 70.88, should have a z-score of 1.96. Let's find out. That's the point minus the mean divided by the standard deviation. Sure enough, z-score 1.96. So I'll clean this format up. I'll throw it out on Schoology. You can look at it. This is stuff you are going to need to know to make any progress on the Kilgore case.